So, hi everyone, and thank you for joining me today. Uh, Today, I'm going to be talking about feature engineering and processing generally. This is part of the learning series that we started last month. Last month, I had a session on SQL for data science. And today is a follow-up. This presentation I'm going to be going through, it's a presentation that caught my attention, and I like the way it explained feature engineering. I'm going to encourage you, if you are in a place that is quiet, feel free to unmute yourself, contribute. Let's make it as interactive as possible. Today we are more focusing on feature engineering for machine learning. And as you know, machine learning is about data. You need to process your data. And after you process your data, that is when you can apply a machine learning model and to get the result that you want. And it's a shame that no matter the amount of data set that you have, uh, different machine learning models perform differently. There are some machine learning models like logistic regression that once you have an empty row, or you can't apply it. And for some other reasons like that, it's very important for us to ensure that we process our data properly. And part of processing the data is also understanding that no matter the amount of data set that you have, not all your data sets will be useful for machine learning. So you need to be able to carefully identify out of the uh, too much data sets that you might have, which particular feature, which particular columns is useful for the insights or the model that you want to build. And that is why it is very important. And that is going to be what we are going to be focusing on today. So I think I've talked about this. And you see, I know I focus more on the machine learning side of things. Uh, Feature engineering, you can apply it in almost any field. In this particular presentation, the focus is more on medical use cases, but this is not limited to a medical use case. One of the, let me say, the experience I had with feature engineering, where I have to go back and try as much as possible to extract as much feature as possible, was actually a project in the oil and gas industry. That's when I was working on BP's global physical catalog. That is the database that's where BP have all their oil and gas data sets, all their oil wells and data sets. And it has about close to 500 columns. And when I'm trying to classify the data set, not all those 500 columns is useful. So I had to go through a lot of work to identify which column uh, is useful for that particular data set. And that's what it's all about. And in terms of future engineering, obviously we have different technology foundation. I'm not going to be focusing on that today. Uh, uh, no matter your data source, you apply feature engineering after you got your data to the platform. So we won't be focusing on the data source. Either it is from an API or SQL, doesn't matter. And even when it comes to the format of your data sets, as you understand, once you have your data frame, it doesn't matter which format. So that doesn't count as well. So I'll just go to the next slide. This slide is just to remind you of data science process. The first thing is you want to understand the requirements, why you need to build the model you are trying to build. And after that, you have to look at how are you going to get the data sets. Unlike, we know that on Kaggle, we have all these process data sets that is ready to use. Real world data set is not like that. Sometimes you have to think about where you are going to acquire the data sets. It might be a data set that you have available online. It's sometimes you might need to pay some provider, maybe Trustpilot, to get data set from them. Uh, It might be within your a particular government department where you work, and you need to contact the data owner and follow all those processes around data governance and the likes. But what I'm just trying to pinpoint here is that you go through that data acquisition and then data preparation. So inside out of as part of data preparation, that is where you have your feature engineering. Because as I said earlier, it is quite important for you to do the feature engineering at this stage because some model uh, will react if you don't have the right amounts, if you don't have it in the right way. And when you talk about data preparation, the first thing you do is exploratory data analysis. That's when you explore your data sets. Uh, in terms of quality assessments, this can vary from organizations to organization, but it is quite important. And it's also part of what we do in data science. Uh, During your data quality assessment, that is when you check how many data sets do you have for each particular feature. Sometimes if you don't have enough data sets, you might not be using that column. It might be that you have to drop it. It might be that you have to apply some techniques to that. And also in terms of data cleansing is part of what you do because a lot of people will tell you that their data set is clean, but by the time you get to the data set, most of the time you discover that you need to do some cleansing and sometimes standardization. For AI, you might need to do some labeling, either manually or using some tools. Imputation is when you are trying to replace data set. Maybe you want to replace with missing column with mean, median, mode, or any value that you choose. And then obviously feature engineering, which we are going to be dwelling a lot today. And who needs to do feature engineering? Uh, we have data engineers, domain experts, data scientists, and also data analysts. The reason why I'm going to add data analysts to this mix is that the line between data scientist, data engineer, and data analyst, I think those three, the lines between them are very thin. In some companies, I see a lot of data analysts performing the role of a data engineer, and some of them also performing the role of a data scientist, especially in consulting companies or in organizations where the data team is not so big and they overstretch. So based on that, I would add data analysts to that mix. I'm going to be following the chat. So if you have your comments, if you don't want to unmute yourself, feel free to put it in the chat and yeah, and I'll respond to it. So what is data preparation? Data preparation, as I said, is a very important process. The, if you are spending 100% on uh, on data science, I would say a data scientist will spend about 60 to 70% of their time on preparing the data. And that is why it is quite important. It can make or break the ability of your model. Uh, Recently, I was supporting a PhD student that is doing some data science work, and uh, she tried to simulate replacing missing data with mean and also replacing with median. And the difference is that for that particular data set, it's the output is different. So that's just to say the impact a particular decision in your preparing while you're preparing your data can affect the outcome of the model. So it is very important. We need to look at it. We need to spend enough time in this phase because if you don't spend enough time in this phase, then uh, you won't get the desired outputs in terms of results. And this book of Applied Predictive Modeling by Max and Johnson, it's a book I'll recommend for you. So during the data preparation stage, it's very important for you to do as much experimentation as possible. This stage is not to be rushed. You need to iterate and iterate. Don't rush it. Because if you rush it, then you have to come back and yeah. So data preparation, importance and motivation. As I said, if you look at this chart, what data scientists spend the most time doing, you see, if you look at refining algorithm, because at least that's what people shout about when you hear data scientist, the model. You see that it's just about 4%, and where you have cleansing and organizing data to be 60%. And that is the reason why we are now having an increase in the number of data engineers that we have, because more people are now moving to data engineering because organizations are realizing that without processing data effectively, it is useless. So you need to have the right, you need your data to be prepared before you can get the best out of, before you can get the analysis, before you can get the best model out of it. So you can see building training sets is just 3%, collecting data sets, that is 19%. And do you know why that is 19%? You would have just imagined that it is just getting the data sets. But there is a lot around getting the data sets. Sometimes, especially when you are dealing with sensitive data sets, for example, you need to complete data governance, of completing the hardback, there are loads of processes around collecting data sets. And sometimes in organization, a lot of insights that many teams might achieve with data sets, but they just can't get that approval to use that data set. And that's just the reality we have to cope with. So if you look at it, you see that 60 plus 19, that's about 80% on just cleaning, organizing, collecting, not really doing stuff that we would call the sexy thing. And that's very important. And that's how I would like you to take this process serious. Because imagine if 80% of the activity is not actually leading to outcome. And I think have anyone have anyone heard about Pareto principle? Just give a thumbs up if you've heard about Pareto principle. Oh, thank you, Savia. And each time I look at data science, I tend to come back to it. I heard about Pareto principle while I was doing a master's degree in advanced engineering and management. That is, but what Pareto principle says is that you only spend 20% of your activity, 20% of your efforts will lead to 80% of outcome. And I think it's the same in this particular instance as well, because it shows that the real 20% on refining algorithms, on building training sets, on mining data patterns, uh, those are the ones that is giving the 8% output. So we need to find a way to ensure that we don't waste so much time on cleaning, organizing, collecting, those stuff that they are nice, they are very important, but they are not the real deal, if I may say. So, and if you look at it in terms of activity, you can see exploring the data 10%, cleaning 20, feature engineering 25, algorithm selection 10, model training, and others. So I think I've talked about this, why data preparation is so important. This particular, as I said, this presentation is for healthcare. So in this particular instance, they are just talking about how preparing the data make a difference in this particular instance. So I wouldn't spend so much time on this. So the next question is, what are the data preparation steps? So if you and you can get that. I think it's somehow straightforward in data science. It's more like see and do. You see, how do I clean up the data? The step is data cleaning. Uh, how to provide accurate data. That you do that when you are doing data transformation. And then how you can incorporate and adjust data, that's integration. Unifying and scaling data, that's normalization. And then how do you undo missing data? That is the one you do missing data imputation. And of course, you can identify and manage noise in your data sets because your data will always have uh, what name shall I call it? There will always be random data sets that are not useful for your analysis. So you need to be able to get the noise, the anomalies in your data sets. So to prepare your data, there are three process to that. The first is for you to select the data, and after selecting the data, you preprocess it and you transform it. That gets you for data science. But if you look at the image that we have here, you can see how everything goes. You see from understanding the main thing. One of the reasons why projects fail generally is that people want the shiniest object, a shiny object, and they don't spend enough time to understand all the processes around it. And it is quite important for us to make sure that we don't rush. So it's very important for us to understand the business. What is the business trying to achieve? This model that I want to build, what is the business question? And when by the time you understand the business, you might not need a model. Sometimes some organization build model that instead of building a model, you might first ask yourself, is this something that you can achieve using some set of rules? Because you can, with programming, you can write codes that can do something at a particular time. And you know that you do it 100% instead of building a model that might be 90% or 80%, So you have to ask yourself, do you actually need a model for this? And by the time you understand the business problem, that is when you go to understand the data itself. The understanding the data will influence how you are going to prepare it. It will influence how you are going to do the feature engineering, how you are going to discover new features. So if you don't understand the business and the data, then it is nothing. But the problem that we do have many times is that due to pressure and delivery demands, data teams will be forced to start to go straight into the data, not spending enough time with the business and data itself. So each time we are working and we have that temptation, we should always remind ourselves and go back to actually understanding the business and the data. So when you are selecting the data, I use that example for you of when I was working at BP and the data has loads of columns, and it's very important for me to choose columns. So it's very important to have people that understand the data sets. And that I meant the real SMEs, subject matter experts. Uh, there is this analogy I normally use. I don't know if I've said it here before, but for those of you that you're very, I don't know, Gary and Xavier, you are quite regular here. So yeah, it's just if you want to calculate the length, the area of a square, instead of building a model to predict the area, sometimes length times breadth is well established, right? And we always give you the correct answer all the time. So having a subject matter expert might save you time because it might just tell you that no, this is not useful. Instead of spending loads of time and then discovering that there is already an established, a well reliable, fast, easy way of doing things than actually building a model. So, and these are the question that is recommended for you to ask. What is the extent of the data you have available? For your model to perform well, it needs to, you need to have enough data. And I mean quality data set actually. But sometimes you can have loads of data sets that is not useful, but you need a lot of useful data sets. And so you need to know the extent of the data that is available. And that is a major challenge in research because sometimes I remember while I was doing my PhD, I had to get some anonymized data sets for my experiments. So, and it's not like if you have a real data set. And then what data is not available that you need to have available, because if you know the data that you have, if you can think about the data set that you might have, because sometimes if you know the data that you want, you might speak to people and they might help you get the data sets. And the thing is, the data set might be available just that you don't know that it is there. So sometimes knowing what is not available, what you think might help you is also useful. And also knowing the data you don't need to address the problem. After you have all those data set that's available and the likes, you need to be able to narrow it down. Because again, not all the data sets that you have might be useful. And just because you have the data set doesn't mean you need to use them. So it's very important for you uh, understand which data set is useful, which one is not useful. I was looking at the data set last week, and uh, there's an example of uh, a data scientist that made a mistake uh, in the insurance company. He made a mistake of adding the column name to the data sets that the model used to predict. And what happened is that the model discriminates against people based on their names. So, obviously, there is no business adding a name to the feature. So it's just knowing that what data you don't need to address the problem is quite important. Because if you make the mistake of adding a data set or a feature that you don't need, then it means that uh, instead of you solving a problem, you might be adding more problem. So better data will lead to a fancier algorithm. And this is correct. I was giving you the example that sometimes some models, when you don't have complete data sets, you might not be able to apply some data set that you need. So it is very important for you to have the data in the right formats. And then apart from that, you need to fix missing data. Because when you have columns missing, you might not be able to apply some model. And also, another thing is that if you don't have enough data sets, it might not be able to address the problem that you need to solve. Just imagine, let's think about politics here. If somebody wants to if someone wants to make like all this survey that they normally do about public opinion, I will assure you that if you do a public opinion in London and if you do another public opinion in, let's say, Liverpool, you are going to have a different result. Or okay, don't let me say Liverpool. London might be depending on the place. Let me say if you do it in Bristol and if you do it in Liverpool. And the reason why I've done choose Bristol is that I chose a place that is conservative and a place that is Labour. So because people will choose to live in their reality. Oh, thank you, Jane. So, so it's quite important for you to understand that disparity in when you are getting your data sets. And what you do to solve that is that you ensure that you have diverse data sets. You don't just focus on a particular site. So you need to make sure that you have all the data set that you need. Also, you need to ensure that your sensitive information in cases where you need to. There are some data sets that are sensitive that you want to anonymize. And one thing about anonymization, most times those sensitive information might not be, well, it depends. If you're anonymizing data based on them being personal data sets, I would say they might not be adding to your model anyway. But in some financial modeling, you might want to anonymize some financial data sets as well, for those people working in finance. And then you need to identify incomplete, incorrect, inaccurate, or irrelevant part of the data sets because that might help too. Because if you know the class, the category that might not contribute to the problem, I think it's better because if you leave them there, they are going to be what we refer to as noise. And as much as possible, you want to reduce noise. And also there is the aspect of more selected data available than needed. One thing is, it's true that when you have more data than needed, you have longer running times for algorithm. Uh, but that one is debatable because it might just be that you provide more resources. Yeah. Because if you look at all the LLMs that we have, I think, is it Llama that is trained with billions of data sets? For some models, the more data sets you have, the better trained they will be. So yeah, so it's something that you look at. One thing is that sometimes it's not one size fits all. So you might need to consider your own particular scenario. But most times you need more data. So yeah. Although I would say for guys working in health, they might do with small data set because they do a lot of statistical analysis and probability and all those kind of stuff. But I would still feel like if they have more data set, it will make their life easier instead of the probability and because at the end of the day, probability is uncertain. So that's a level of uncertainty introduced to the data set either way, and that's bias. Yes, many times we dummy variables, and the dummy variables is used most times when you are trying to impute missing data sets. So yeah, so what you do is you have all our categorical data sets. If you have, for example, if you have yes, no, the computer will only understand numbers. So because of that, it has to be converted to zero and one and the like. So a process that is used is using all these dummy. So you can use full dummy, and then you can have your dummy representing categorical variables and with them. Yeah, so one thing about this is that it's it's one of the ways where you replace missing data. So there are other categorical variable. There is one hot encoding. There are various ways. But one thing I would say you should look at is if you look at the one we have, when you have a dummy variable, it's what it's saying is that for each particular scenario, you can say when it is small, it's giving one and it gives other zero. When it's medium, it goes like that. And in this particular case, they are referring to, you can see the different scenarios. Sometimes there is a full dummy, and that is the most popular one, the one hot encoding. It's quite popular. The reference group, I've not used it, but it's possible for you to use it as well. And as you can see in the diagram, they are trying to show the difference between the full dummy and the reference group. I can't really say what's the difference. I can't explain in depth what difference is, but as you can see from the diagram, it shows that when it is small, there's going to be a reference group that will be the real reference. So in that case, it is zero. And then we have values for x1 and x2 when it's not the reference group. So I would say maybe, yeah. And then for the dummy variable with ordered category, it's more of 0, 1, and 1. From this, what I can say is that I would still recommend the one-hot encoding because one-hot encoding is seeing each one as one. One thing we need to be careful when we are replacing variables is that sometimes when you are replacing a variable, the algorithm might see zero as less important to one or two. I don't know if you get what I mean. The algorithm might, if assuming you have uh, ABC and you replace it with 0, 1, 2. Some algorithm might feel is uh 2 is bigger than 0 or is more important. And in that case, the algorithm will favor 2 and 1 more than 0. So that's why you need to make sure you use an algorithm that will see which as the same. It's only if you have a situation where you have maybe disagree, agree, strongly agree, and you actually want that kind of, how can I say, sentiments. But most times you might not want those sentiments. Please feel free to add comments and thoughts as we go along. It's nice when I have opinions and that might be something that will benefit from having few people on the call. So data transformation, in this particular instance, we are looking at the transformed attributes. If you look at the raw data, and the log transform data, you can see that the raw data is scattered, but after applying the log transform, we have a data set that log transform brings out a particular pattern that we might not notice without it being log transformed. So, and there are different kind of transformation. There is linear and there is non-linear. The log transform is applied here when the data set is non-linear. So that's an attempt to find hidden pattern in the data sets. And there are different other ways in transforming data sets, but this is useful. It has some mathematics behind it, but the good thing about this is that you can do this with Python or R. Programming has make it easy. You might not understand the fundamentals behind it, but you can just write the code. But what I would say is it's just normal taking a log of a number. You have the real value, and then you just say log of this particular value. So that helps to reduce some noise as well. So I'll call it noise. And I hope I don't overuse noise today. And still under transform, it leads to this as well. That log transformation, they said is suitable for you use it when your data is filled. So as we said, because the data is filled, you apply that log transform to normalize the data sets. And in this particular instance, they have logarithmic and the square roots. Both of them are focused on improving right screwed data. While I was looking through this slide, I was thinking what happens when the data is left screwed, as we have in this image, but I didn't get to it. So if any of you know in the comment, and please put it in the comments or feel free to talk about it. Because yeah, I'm sure there's something for left screwed data sets. So how do you handle missing data? Data sets, the problem regarding missing data will always exist. If I give everyone on the call now a particular form to fill, if I put your first name, your last name, your title, I just put something, even if it's just 5 questions. Unconsciously, you notice that some will omit some columns. And when that happens, and that's what happened in reality when you are trying to get data sets. Due to mistakes, omission, everything, something just happened and some data set is going to be missed. So this is a problem that will not go away. The best thing is for us to think about how we can solve it. If you look at the image here, it shows different ways by which you can handle missing data sets. Sometimes it depends. You have to look at it. What problem are you trying to achieve? Sometimes if you have a data set that is not, let's assume you have a row, a column that has, if 50% of a particular column is missing, or maybe 70%, it might be easier for you to just delete. So you need to think about, is it what, based on the amount of data that you have for a particular feature, is it worth using that feature, applying it in your model? Because just imagine if you are having to use mean or median, and what you are replacing is more than the real data set that you have. So, but if you are deleting, you can be deleting some rows, you can be deleting some columns. So you have to think about, and I think it might be difficult sometimes to make that decision to not use a particular column, probably because of maybe your knowledge or anything. But that is something that you actually need to consider. And in cases where you've decided that no, you can make use of this row, you can make use of this column, and then you want to consider how you can so what you can use. So that now leads to imputation. And for imputation, it can be time series or it can be the general problem. If it's the general problem, you are thinking about if it is a category or if it is a continuous data set. When it's category, you might be thinking of maybe replacing it with not if the data is not available, are you replacing it with another text? Are you replacing it with the highest occurring text in your data set? So you have to think about which one you use. One thing I always advocate for is that when it comes to your missing data, don't just maybe apply mean or median or mode and just move on. Do some experiments. Try using mean, try using median, try some things and see what is the outcome. So because I believe that if you do your experimentation and you can choose, okay, based on trying this and this is what I think give the best results. I think that is helpful. But on a general note, I know more people tends to make use of median when it comes to uh, continuous data set, for example. And then data imputation, mean median, and that's the way it is. If you look at the table on, as I'm looking at it, it's on my left. I hope it's on your left as well. You can see it has some NAN. Those are column that is missing. But in the column on the right, it has been replaced uh, with the with the mean. That is the mean. 5 divided by 17. Uh, 5 plus 17, 22 divided by 2. Uh, Although interestingly, it's not, yeah. So, and then if you look at column 3, uh, it's also replaced with mean. But I don't know, but in this example, it looks like both is the median and also the mean. Who also noticed that? So, but yeah, and that's it. But let's look at it. What are the advantage of this? The pros, easy and fast, and it work well with small numerical data sets. The problem with it is that it doesn't factor correlation between features. It will give poor results on encoded categorical features. It's not very accurate. It doesn't account for uncertainty in the imputation. One by has example I usually give is that if you have a 90-year-old man in a grandpa that is 90-year-old in the house with maybe grandchildren age 8 and 5. If you use average or median, the average will be 90 plus 8 plus 5. So that is 98, 103. 103 divided by 3, that is 30, around 35, 34, 35. So, and we now say we have an average of 3 young men in the house. So, that doesn't add up. And that's some of the challenges with this. And they are real challenge especially when you are dealing with sensitive data sets, especially for those of you in in the health industry, where getting it wrong might means that somebody that is supposed to be diagnosed with cancer is not diagnosed on time, and it is life-saving solutions. So yeah, that's something we have to look at. But then it's just about us experimenting and trying things out. And this is another one, data imputation. So this one, most frequent statistical strategy to impute missing data. So it's replaced missing data with the most frequent value within the column. They said it works well with categorical feature, but again, it doesn't factor correlation between the features. And the biggest of all is that it introduces bias in the data sets. And the bias is that it favors the more popular candidates or the most popular class. And that's one thing we have to be careful of. Well, for majority that will be proponents of democracy, you might say majority carry the vote, but in some instance, that is not the case. Each class needs to be represented as much as possible. Another one is k-nearest neighbor. Yeah, and that is using machine learning itself. And with k-nearest neighbor is using similarity to predict the value. So, and what it does is it finds the average of closest data points and then use that to use that. One thing about it is that it's accurate than mean or median and most of the methods. But the thing is, this is like running a machine learning within a machine learning. So in terms of computational cost, it's more expensive. And one thing about it is that it's sensitive to outliers in the data set because when you have those outliers, it will screw up it will screw the data sets. Because it will affect the mean or it will affect the average of the data point that is closest to that particular point. So, but what I would say is that even though this particular method is computationally expensive, it's looking like running machine learning model is becoming more affordable. And I think it's going to be becoming more affordable as time goes on. Because right now we have, you can, there are a lot of platforms where you can run your models for free on Kaggle, on Google Colab, and other platforms. And I believe that more platforms will be coming up. Currently, I see that the platform I'm waiting to drop in terms of price is platforms like Databricks and ADF and Synapse Analytics, Snowflakes. I'm still expecting, I'm still waiting for them to come down because currently with their prices is still not so affordable for individuals to subscribe and try things out. But I hope we get there. But I believe that we are getting close to that. And this is another method. Uh, have I talked about this? Okay, 1 second. Get most frequent or zero constant value. Replace the missing data with the most frequent within each column. Yeah, so that's still like the median. So again, when you just replace the missing data with the most frequent, definitely that's bias and that's a real challenge. One thing is there will never be a perfect way to handle missing data sets, and it's okay. And that's the thing. That's why feature engineering, you have to spend a lot of time trying it. Okay, I think I've passed. Okay, I must have mistakenly go back. So, and there's another one, multivariate imputation. And in this particular instance, filling the missing data multiple times. It is believed that this is better than single imputation that is measures uncertainty in the missing data. But I've not really tried this, but it looks interesting. It's something that you can try. Uh, if there's anyone that have tried this, you can let me know in the chat. But the thing is, what I say about this is that instead of applying the imputation once, you are doing it multiple times, so that when you do it, it's just to reduce the bias and get more have maybe to reduce the uncertainty and have an average probably. So, but let's see what is here. Okay, we have age, income with mean imputation 25 and okay, average. Okay, so yeah. Data reduction. Data reduction is another option, and as we know, sometimes it's necessary for you to reduce the data sets. One method I've used in the past to reduce data is through feature importance. After doing feature importance and understanding, looking at how each feature contributes to developing the model, then removing columns that I think are in the negative. And I think you can do feature importance using random forests and SGBoost. At least those are the two I can know. Yeah, but you can look at other ways to do it as well. But so it's very important for you to, because sometimes, as you said, having too much data can be a problem because some features might not be contributing to the solution you want, and also the fact that the features might be introducing noise. So how do I reduce the dimensionality of data sets? That is through feature selection. By selecting the features you can reduce, that is you manually not ignoring those ones that are not useful. Another, how do I remove redundant or conflictive example? That's what they call instance selection. And how do you simplify the domain of an attribute? They call it discretization. And how do I fill gaps in data sets in data? That's feature extraction or instant generalization. You can do the feature extraction or instant generalization using some mathematics. I think it's quite useful in image processing. That feature extraction and instant generation is it's used a lot in image detection. So, and again, I know I'm introducing you to all these different methods. It's not all the method that you would need in all the data set that you are dealing with. So it's more of you having a toolkit that when you need, you know that it's there for you to use. And there is PCA as well. And one thing about PCA is that, as you have a lot of data sets, it's very important to ensure that you have a way of discarding some dimension in such a way that you don't lose key information. And that's what PCA does. It helps you, the model itself will choose uh, those dimension that contribute most to your analysis. So, and instead of you doing it manually, PCA can do it. And the good thing is that you can implement it with Python. So you don't have to understand, you don't have to go too deep into the mathematics, but it's something that you can do. And it's reduce the dimension and help you uh, in terms of preparing your data for your model. And when you do your PCA, it might means that your model focus more on the important information that you need instead of training it on noise. So it might help you to improve your training. So, and how can you apply it? The advantage of it is that it removes correlated features, improve your performance, reduce overfitting, and improve your visualization. But as I said, see, there is no one size fits all. It has its own disadvantage. When it is as it's focusing on your key information, it's possible for it to also lose some information because the model might think the information is not useful. It might turn out to be an information that is useful as well. So there will be that information loss. And there is the fact that you need to do your standardization before you use PCA. For those of you that you are familiar with Python, you can do your standardization using standard. You can use scaling. In Python, there are kind of scaling. We have the min, max scaling. There is the normal scaling and standard scaling and the like. So it's just making sure you do that. And then this one, independent variable become less interpretable. So let's go. Fourier transformation. I actually thought I'd remove this particular slide, but this Fourier transformation is some mathematics. I did this actually while I was doing a master's degree in there's a course digital signal processing. So where we use a lot of Fourier transform. And one thing about this is that it's in real life, most of your data sets are not as linear as we might want you to believe. So it's not a straight line. So it is very important. So using mathematics like Fourier transform help in terms of giving patterns to your data sets. And this is an example here. So Fourier showed that any periodic signal can be written as a sum of sine waves with various amplitude, frequency, and phases. So This is Josephoria that discovered this. It's quite useful, but I wouldn't dwell so much on this if you are a beginner in this area. It's more into digital signal processing and all those kind of stuff. But the most important thing is that you get a pattern out of data. I would say it's more useful for guys that are working in a domain that requires a lot of signal inputs and function response function. And I think recently I was chatting with a guy that has attended our this meetup that is working with energy, and they do a lot of this in energy. Okay, thank you, Mark. Fourier transform useful for extracting seasonal pattern from time series. So it's useful for time series as well. But and then back to something that is very important. It's very important for us to understand the relationship between variables and attributes in our data sets. Because if we know how each of the data sets depend on each other, sometimes we might even get insights without doing machine learning or anything, because we can see that it's just, I think I was chatting with someone recently. I was looking at a particular data set about water analysis. And when I saw, when I saw calcium and I see magnesium, my knowledge of chemistry tells me that calcium is a strong cation. It's easy to react with a strong anion. Sorry, is an anion and reacts with chlorine that is an anion and that is strong. The -1 and +1. So sometimes when you finish your feature engineering and you get some insight, it might be easier for you to come to some conclusion based on your existing knowledge, and nothing beats common sense. I used to say it that if something doesn't make sense, if it doesn't make sense to you, it's likely that it doesn't make sense. So with that, you should test that logic. It, sh- it should be understandable. You should don't see it as a black box. See it as something that can be understood. So, and then with correlation, you can, and then I think the popular one that I would say here is that I think people with the statistics experts will like to say that correlation is not causation. So something might correlate. It doesn't mean that is responsible for a particular outcome. So we need to keep that at the back of our mind. So autocorrelation, this is in time series, heavily used in time series and forecasting. So this measures the correlation between lag values and time series and obviously uncover hidden pattern. So yeah, and okay, so 1981 to 1990, and then, so yeah. So we can see here there is convolution, cross correlation, and autocorrelation. So I think, so one thing we can look at here is that based on your data set, you might need to apply a different type of correlation. Again, still going back to the point that it's more of, you might need a lot of in your feature engineering, it requires a lot of experiments. So trying things out. And we need to be confident about that. It's okay to try it. And then transforming data. I know I've talked about, I quickly make a reference to scaling the other time. So scaling is quite useful because sometimes if you have, let me give an example. Let's assume you have some numerical data sets that has 1,000 and the same column has maybe five or six. If you don't scale, the model will tilt towards the bigger value. So that's why you need to apply that scaling and the like. So I don't know if that explains it. So scaling helps. I would say again, the word I don't want to say too much. It removes some noise and through standardization. And then we have the decomposition, when you have there may be features that represent complex concepts and may be more useful to a machine learning method. So, an example of that decomposition, I think we do it a lot. For those of you that you do a lot with Power BI, if you have your dates, you might split it into different columns, and then it might give you an extra insight. You might discover that maybe some things happen in June that doesn't happen in December. I know for those of you that you grew up in the UK, you might not experience this, but I grew up in Nigeria and we have two seasons, rainy and dry season. So because we have a lot of rain in, let me say, June, July, August, uh, if you use if you try to use, for example, maybe rain data set, for example, you'll notice that there will be difference in the amount of water level in June, July, August compared to, let's say, December, January, February, which we have little or very little or no rain. So, all those things. So splitting it a little bit, it might help when it comes to identifying trends in the data sets. And obviously, aggregation is a feature that is quite important. And in data engineering, your bronze, no, your gold layer is most times an aggregation based on business logic. So it's quite important to understand the aggregation, and many times you aggregate based on understanding your data model, your schema. If you are using facts and dimension, you have to establish the model, and then you can get the right aggregation for or to get the right insights that you need from your data sets. So again, we've talked about standardization, but this is just looking deeper into standardization. There are different kinds. Some standardization is between 0 and 1. Some is from 1 to -1. The most important thing is for you to look at which one works best for your data sets. And I would say when it comes to choosing a standardization method, I'm sure there might be some things that you consider. But I would say in most of the ones I've done, I've usually just go for I've tried two of them, the minimum, maximum, and the standard scaling. I've not tried others outside of it. If you've tried more, feel free to put it in the charts, your experience and what impact it has had. For me, most of the time, I've applied scaling because if I don't scale, uh, I, I would have issues building my model, especially when I'm dealing with, uh, let me say, linear regression or regression data sets, regression models generally, and also like logistic regressions too. So feel free to share your experience. And okay, I've mentioned this. If you look at it, the difference between both is in terms of their mathematics. You can see x minus minimum x over max x minus minimum x. Again, you won't have to do this manually. It will just be you. Uh, it's part of scikit-learn. So all you just need to do when you are using Python is for you to import. You import scikit-learn, and once you import scikit-learn, it comes with all these modules. And why do you scale? If you look at this, you can see with scaling, KNN without scaling, KNN with scaling. No, what I would say is, I don't know, it looks like this is a different image to the one I want to show. Okay, this is what I want to see. So without scaling, you can see that you can see this red that is very close to blue. And but when you scale give that boundary. What you can say is that this blue that is in the red side is definitely an outlier. And the same thing applies to the red in this blue side. So without scaling, you can see that it's difficult to demarcate. But when you scale, it gives this pattern to it. So that's why it is important for you to scale. And again, remember the analogy of 1005, because if you have bigger numbers, the model automatically tilts towards the bigger ones. So, and that's part of what is happening here. Let me go back. Okay, because if you see, you can see 8,000, 9,000. You see, after scaling, it's giving -2 to 1.5, -1 to 2. So you can see. So feature engineering, yeah, I think I know we've been talking a lot about it, but we are now talking about it in particular. It might be difficult to come up with a new feature. For those of you that you are using Power BI, I think that's one thing I like about with DAX and everything. It's like I can say an application of creating a new feature. Creating maybe a column for some based on adding another two columns. I think that's basically what it is. But one thing is it requires an expert knowledge. You need to understand your data set quite well. And for you to do feature engineering, what you need to understand what data you need that you don't have. That is the answer that you answer when you start generating a feature. Because you have to imagine, if I have this particular data set, will it make a difference to my data set? And that's when you start thinking about creating those features. So the feature you use influence more than everything else. It will influence the results. So yeah, so it's very important for us to spend time with this, to think about this. And one thing we need to understand about this is that it requires expert knowledge. So when you are building a new feature, don't just do it on your own alone as a data scientist or a data engineer or an analyst. Speak with the business. Ask them if the feature you are introducing, if it makes sense. Just because you can do something doesn't mean you should do it. So you can ask them, speak to them. If you have this, what impact will it make? And yeah, and with that, you help. So and again, you can see when the, the image is just showing you where the feature is. From raw data, you get your features, and that's where you do the feature engineering. So there's this book I have. If you want, I can share. I downloaded it online anyway. I have the soft copy. If you want, I can share it with you. It's basically around feature engineering and different principles and techniques that can be helpful to you as a data scientist. Because at least we can see that it's quite important for you to have the right features for you to get the best results, the best models. So on that feature engineering to make reading of the data easier for your machine learning models, yeah. And also feature engineering is the process of transforming the given data into a form which is easier to interpret. So if you look at all that is here, it shows you why you actually need to do this. It's quite important and it's not something that you should rush. What is this? Am I going back? 1 second. I don't know why I don't know why this go back. My mouse. It's not reacting. My mouse is not reacting. Okay. It's now reacting. You see. Okay. So yeah, so let's look at the aspect of feature engineering. There are different aspects. I would say it's not even the easiest, but I can say select a feature selection. That's the first step. That is when you are selecting relevant feature from the available data sets, uh, based on what you have, and it depends. I would say for selecting feature, it's a combination of expertise, subject matter expertise, and common sense. But sometimes with common sense, you can know that, oh, this particular feature cannot work. And then feature extraction, that is when you use existing features to develop new ones. Example, when you use length and breadth to develop another column that is area. So that is using existing features to combine new one. Or instances where you do a log of a particular column. And then feature addition, new features are created by gathering new data sets when you get new data sets. And you can also extract new feature based on current data sets. Recently, I was going through a particular data set on a medical data set where they got a column for not smoking. All the children that have age less than 10, they were classed as as not smoking. So, that's using knowledge of the fact that maybe a 10-year-old is too young to smoke. I don't know if that assumption is still real with the current dimension of our community, but I would like to believe that is still correct. So, and then feature filtering, you can filter out irrelevant features to make the model step easy. I've not practiced feature filtering. If you have practiced it, feel free to talk about it or please in the chat. That would be great. So, but one thing I would say is that either we know it intentionally or not intentionally. I think everyone on this call have done the first three: feature selection, extraction, and addition. We've done it in some ways. So yeah, so and that's it. That's why I used to say some of these things is just something that we are doing, just that we don't know that is what we are doing. So it's good that we are putting more at giving it more attention. And this is Machine Learning Mastery. That is a website I spend a lot of time on. It has a lot of good information, and I would recommend that you check it out. So it's saying how to choose a feature selection method. So those are the things from input variable. You have to decide if it's a numerical or categorical, and then next to the kind of output variable and the like. So yeah. So, and it's good if we follow all these steps. So, and with that, you can know if you are having a relevant feature in your data sets. Because I want to believe that the features in your data set will either help you to get a good model or disturb you from getting a good model. I will believe that your feature will not be neutral. So either add or remove. And if we can identify the best set of models, then it means that it's easier for we get the best model and outputs. So what are the benefits of feature selection? It reduces overfitting. So we have less redundant data sets, and it means that we have uh, when we have an opportunity to less redundant data means less opportunity to make decisions based on noise. So we are able to make decisions based on facts, and then improve accuracy. Less misleading data means modeling accuracy improves, and then reduce training time. Less data means that algorithm train faster. Yeah. Imagine if you understand that your model is only making decision based on some 5 reliable columns, and you only train your data using those 5 columns instead of focusing, getting about 100 or more columns. So, that would make a huge difference, both in time and resources. And feature extraction, as I said, is mostly this particular one is an example of image processing. So, when you feature extraction aims to reduce the number of features in the data set by creating new features from the existing one, and then it discards the original feature. So it highlights features that are useful, and then with that you get it means that you focus on what is useful, what is rich for your data sets. So the new reduced sets of features should be able to summarize most of the information contained in the original sets. And then these are some books on feature extraction, uh, if you are interested in researching more into it. For those of you that are interested in image processing, it might be something that you would like to look at. And again, feature engineering is applied as a mark, as you've put in the chat, Fourier transform being used for to extracting signal pattern from time series. You can see that feature engineering is used for time series, and it's used quite a lot, especially when it comes to Windows feature and lag feature and daytime features. So if anyone is working on time series data sets, it's something that you should definitely look at. And what I would encourage us to do is to automate feature engineering. And it is possible for us to automate it. Because if you automate feature engineering, and then if you notice which features you need, you can make that process to be done by your data engineers. So that when the feature engineering and everything is done, and then you train your model, it means that each time you are calling your model to predict, it's not going through all the process of doing all those process. And it means that your model can predict, especially when you have a model that you want it to predict in full time, in real time. Imagine you are a bank and you have a credit card and somebody needs to make a decision on a credit card. If someone fills their information and they click submit, you should be able to come back to them in few seconds to say rejected or accept. So, and for your model for customers or service users to get the best out of your machine learning products, it is quite important for you to make sure you find a way to automate this feature. And when you automate it, you put it as part of your data transformation or data engineering process, so that each time you need to predict, it doesn't go through that cycle of processing. So and yeah, so as you can see, it is useful both for machine learning and for deep learning. And I think this is where I think I'm getting to the end of this. So what is just saying is that it's useful for either you are doing clustering, classification, no matter what you're doing, uh, feature engineering is useful and it is something that you should embrace. So a summary of this is that there are three steps that is important: data selection, data processing, and data transformation. So those three processes help you to prepare your data sets. And at the heart of the process in your data preprocessing, that's where you have your feature engineering. So thank you for joining. And that is the end of today's uh, learning session on feature engineering. Thank you, Savia. And thanks, Mark, Gary, uh, Bamidele, Polani, and Patrick for joining. Thank you, Mark. Thank you, Tolani. Yeah. So, and we have a face-to-face session in Glasgow on the 18th of July. We have two guys that will be coming to present from Barclays. They will be talking about their interesting work they're doing at Barclays. So if you are around Glasgow, feel free to join. It's going to be interesting. So thank you very much and enjoy your evening. Thank you. Let me stop recording.